Hello students. In this video, I will be discussing the program 11 from the subject Data Structures Laboratory. The subject code is BCSL 305. Let us look at the program statement. It says, develop a program in C for the following operations on graphs of cities. The first operation is create a graph of n cities using the adjacency matrix. Print all the nodes. The second part is print all the nodes reachable from a given starting node in a digraph using BFS and DFS method. Okay, so the program statement is you have to implement graphs, and also in the graph you will have to create an adjacency matrix, and also all the nodes that are reachable, okay, from a given node using the method of traversal method BFS and DFS. So before I start the concept, let me give you a brief introduction about the graph. Okay, so that we will do first. Then we will come to the lab program. Okay, so how do you define graph? So what is a graph? See, this is main thing that you have to understand before you get into the program even. See, graph is a non-linear, non-primitive data structure. Non-linear and non-primitive, as in it is not fundamentally present in a programming language. Also, the data of the graph is not stored. The values are not stored one after the other. That is what it means when you say non-linear. Okay, so how do you formally define graph? So, graph definition goes like this. A graph G, okay, I will denote the graph as G, is defined as a graph D is defined as a pair of, it is defined as a pair of two sets. One set is V and the other set is E. And it is denoted as, it is denoted as G is equal to V comma E, like this. Now you will have to understand what is meant by G, what is meant by E, and all those things. Okay, so see here, V is the number of vertices. V is the number of vertices and E is the number of edges. See, sometimes we get confused what is meant by vertices and what is meant by edge. So let me show you with the help of a simple graph. See here. So if this is a graph, okay, something like this. Okay, I'll name these A, B, C, and D. Here, vertices means basically these circles, the values. These are the vertices A, B, C, and D. These are the vertices. Okay, so vertices are A, B, C, and D. And edges are these lines. Can you see these lines? These lines. So these are called as edges. Okay, so these are called as edges. So graph is basically made up of two things. One is a graph is made up of basically two things. One is the vertices and the other one is edges. Okay, so in graphs also, there are two types of graphs. See, if you look at the question, it says something called as digraph. Okay, digraph is mentioned. So what is the digraph? Digraph is one type of a graph. See, a graph can be of two types. One is directed graph and the other one is undirected graph. Undirected graph. Okay, so graph can be of two things. One is the directed graph, the other one is undirected graph. So for example, directed goes something like this. It looks something like this. See, A, B, C, and D. So when you have these edges, right? So edges will have directions like this. So this is what digraph means, directed graph. So there is direction. See, for example, if I write like this, the edge is going from B to D, but not the either way. That means it is not going from D to B. That is what directed graph means. Whereas in a case of undirected graph, okay, something like this. There is no direction. So the vertex A and B, in that the edge is from A to B as well as from B to A. So this is both the directions. Okay, so you can either so if it is a direction means it shows like this. If it shows something like this, that means obviously it is bidirectional. Okay, so here undirected graph means there is no direction. Okay, undirected graph means there is no direction. Directed graph means there is a direction associated with the edge. Now, I hope this is clear what is meant by graph, what is meant by the directed graph, digraph, and what is meant by undirected graph. Now we'll look at adjacency matrix. Adjacency matrix. Adjacency matrix. Okay, see, when I look at this diagram, okay, this graph, I know that there is a edge from A to B as well as from B to A. Correct. But how do you represent that in the program? How can you show an edge? You can't really write an edge and give it to the system, right? So here we have one representation called as adjacency matrix. So how do I write? All the vertices will act as an index here. A, B, C, D, A, B, C, and D. See, this I'm talking about this one. Okay. So what you have to do is you will have to put either 0 or 1. Okay, here. It looks like a matrix. So you will have to put zeros and ones. If there is an edge between, if there is an edge between the two vertices, we give 1. If there exists no edge, then we give it as 0. For example, look at this part. A to A. Look at this diagram and tell me if there is a edge from A to A. From A to A, there is no edge. So I'm giving that adjacency matrix value as 0. Likewise, from A to B. See here, from A to B, there is an edge, right? So 1. Likewise, A to C. A to C, I'll give like this. Okay. So A to C. From C to A, it is there. But from A to C, it is not there. So like this. A to D is also not there. See, from A to D, there is no direct edge. So 0. From B to A, it is there. See, because it says other direction also, right? So B to A is present. B to B is not present. B to C is also not present. B to D is present. See, B to D is present. So 1. C to A is also present. This edge, C to A. Okay. And C to B, not present. C to D, let me give like this, C to D 1. C to C is 0, sorry, C to C is 0. C to D is 1. D to A 0. D to B 0. D to C is also 0. And D to D is obviously a 0. Usually the diagonals will be 0 itself. Means from A to A, there won't be an edge. From A to B, there won't be an edge. C to C, there won't be an edge like this. Okay. So that is meant by adjacency matrix. This matrix shows you the, if there is an vertex that, if there is an edge that exists between the two vertices. Okay. I hope this is clear. Now we will get into the graph traversal, BFS and DFS method. Okay, so graph traversal. This one is very important. Traversal, I hope you know what is meant by traversal in general. Traversal means like getting to that point or accessing. Okay, so accessing. So you can access a given vertices. Okay, using two methods of graph traversal. One is your BFS method. The other one is your DFS method. BFS and DFS. See, this is breadth first search, and this is depth first search. First, you have to know the full form. Breadth first search, depth first search. See, for example, if I have a graph, something like this. Or I think I'll take out the directions. Okay, wait. From 8, 1 to 2. Let me write like this. It can be directed, of course, in our program it is directed, but let me show you like this. See, if I have to do the breadth first search on this, breadth. So you have to remember the accessing goes in a horizontal way. In a horizontal way. See, I will start accessing from here. So from 1, I will go to 2. Okay. From 2, I will go towards the left. So like this. Then to this. Basically, you have to access the elements one after the other. So here like this. It goes in the like a horizontal fashion. Something like this. Whereas in case of first search, depth, that means height wise it goes. Okay. So it is like vertically you have to go. So if it is like this, it goes something like here. It goes from 1 to 2 to 5. From 5, it goes to 3, then to 6, then to maybe 4, and then to 7. So breadth first search goes horizontally, and depth first search goes vertically. Depth first search goes vertically like this. So when you are implementing BFS and DFS, we have to take you have to make use of another data structure that we know, because we want to make sure that we are keeping track of the nodes that we have visited. So visited as in we have accessed. Okay, so in case of BFS we make use of Q. Remember this, in case of BFS we make use of Q, whereas in case of DFS we make use of stack. Okay, we make use of queue and we make use of stack. Now, queue and stack, I think you know the concept, right? So, front and rear is used in case of queue, and in case of stack, top is used, and so on. See, why stack and queue is used here? See, one thing is in case of BFS, we are accessing the elements. Okay, see, 1, then 2, then we try to check its next value. So, what happens in case of BFS is we try to find all the existing neighbors. So what I will do is, see, first I will go from 1 to 2, from 2 to 3, then 3 to 4. Okay, then I will have to restart again at 5, then 6 and 7. So I would have reached here, then I will have to come back to 5. So I will make use of Q for this one, because every time the current there will be a current value that will keep moving. Whereas in case of stack, only one is used. See, 1, 2, 5. Then I can pop out and come here to 3 and 6. Then go back and then come to 4 and 7 like this. So I will make use of Q and I will make use of stack for the traversal. Okay. And now by now you should know that the value of adjacency matrix and all that, right? So with that, I will try to do the lab program. See here, first let me give the main program. So int main choice, okay, you can either do BFS and DFS. That is why I've given CH as the variable. Then start means you will have to give the starting vertex. Okay, starting vertex. It can be like if there is a graph like this, from where do you want to start the traversal, that you have to specify. So if I want to start it, the second one, you will have to give that value. Okay, so that is one. And because adjacency matrix means two-dimensional, right? So in order to keep track of the indexes, we have I and j. First thing, you give the number of vertices. Suppose you give 5. If you give the n value as 5, then 5 vertices will be created like this. I mean, numbers are not really important, but 5 vertices will be created. Then you create the adjacency matrix to show the direction like this. Okay, so for I equal to 0, I less than n, I plus plus. That means if it looks like this, okay. So 1, 2, 3, 4, and rows are like this. See, first thing is you want to keep this constant, because then it will be 1 comma 1, then 1 comma 2, 1 comma 3, 1 comma 4 like this, right? So you are keeping I value constant, you are going through the j, then again updating the value of I, then doing j. That means you're filling the adjacency matrix row by row. Okay. And initially, see here, I want to check the order at which the vertices will be accessed. Correct. Now the thing is, okay, see, for example, in this case only, see, if I write like this, something like this. Okay, so from 0, I can go to 1. Correct. So if I give the starting vertex as 0, okay, so from 0, if from 0, I can go to 1. So 1, once I visited, from 1, I can go to, let's say, 2. 2 or 3. From 1, I can go to either 2 or 3. I choose to go to 2. So 1, no, sorry, from 0, where is it? I think it is lost because sometimes this zoom feature, okay, anyway, I'll try my best, okay. So 1, 2, 3, and 4. See here, if it is something like this, okay, something like this. See, from 1 to 2, I will go. From 2 to 4, I can go. Now, from 4, I can go either to 1 or 3, right? Now, what if I choose 1? Starting vertex was 1. Okay, so starting vertex was 1. From 1, I went to 2. From 2 to 4, 4 to 1. Now, again from 1, I will have to go to 2. Then from 2 to 4. See, there is a loop formation over there, right? So what you have to make sure is, once you have visited or accessed any of the vertex, next time you shouldn't access that one. But how do you make sure that the system knows that, okay, given vertex has been visited? So what we do is, when the vertex is visited or we have accessed it, its value, we make it as either 0 or 1. When it is visited, we make it as 1. So the next time we don't go to that node. So from 4, I know that I shouldn't go to, from 4, I shouldn't go to 1. From 4, I should go to 3. Because current of 1 would be 1. Whereas current of 3 would be 0. Because that is not existing now. Are you understanding? So that should be maintained first. Okay. So I think it is over here. See. Let me erase all the things. Okay. Okay, anyway. I'll move this only slightly down. That's better. Okay. Uh, we are here. So visitor is initially 0. That means none of the vertices are visited till now. Then you will give the starting vertex, variable is start. Then choice 1 is BFS, choice 2 is DFS, and you will enter the choice. Okay. Then we will whatever starting vertex we have given, from there you will have to do the BFS. That means that is a starting point. From there you do the BFS traversal. So from the start, you start the traversal. Okay, so row by row you will go. If you remember, it has to be row by row, right? Sort of like horizontally you have to go, right? So we are taking that first into consideration. See, I equal to 1, I less than or equal to an I plus plus. Okay, then if visited is equal to 0, so if the visited is still equal to 0, see, we will do the entire BFS thing. All the rows will be accessed. And still, if the value of visited is 0, that means that particular vertex is not reachable from where you have started. You would have given one starting vertex. See, for example, this case. See, 1, 2, 3, and 4. So, what if I given something like this? See, from if I give the starting vertex as 2, if I give the starting vertex as 2. So from 2, I can go to 3 or 4. I'll choose 3. Then from 3, I can go to 4. Okay. Then from 4, I can go back. I can't go back. I'll stay here. So from 2, I can either go to 3 and 4. Correct. So from 2, the vertices that are reachable are 2 and, from 2, the vertices that are reachable are 3 and 4. Whereas 1 is not reachable. So if that's visited will still be 0, right? It's visited will still be 0. So that also we will tell. If it is still 0, we will tell that it is not reachable. Otherwise, this visited would become 1. The value would change to 1. So that will be given by the BFS. Now, similarly, case 2. Okay, from start, then DFS. This is going vertically, right? So one after the other, you can pop the value. So you don't really need, to keep track of the visited and everything, because we are not restarting. We are doing it from there itself, right? Let me show you the logic. The logic is very simple. Let us start with the logic. So first, your adjacency matrix is one input. Adjacency matrix is one input, then the total number of vertices, and to keep track of the visited, we are using this particular variable. Okay, then I told you that for the traversal, we are making use of queue and stack, right? So I have used queue and I have used stack, and all the necessary variables associated with the queue and stack are kept here. Okay, now we'll do the BFS. So we will start at a given node. So that vertex is given. Okay. See, initially when you start, so you are starting here, right? So if it is something like this, if you're starting like this, if you're starting here, that means next time you shouldn't, because this would have got visited. You're starting only from there. So immediately that vertex, we are keeping the visited as 1 for this particular node. I'm making the visited as 1 because it is now accessed. That means it is visited. Okay. And you have to use the queue in order to put the elements into the BFS traversal, right? So yeah, and you know that queue means the insertion is happening at the rear end, right? So once you access that element you put it into the queue by using this particular step. Now, while the front is not equal to rear, that means when your queue is not full, okay, when the queue is not full, what you have to do? See, once you have accessed that element, for example, 1, okay, then what you do is you delete it off and store it in a variable called as current. Okay, see, for example, this one. So here its adjacency matrix would be something like 1 2 3 4 1 2 3 4. So 1 to 1 is not there, so like this you only have 1 to 2, 2 to 3, and 3 to 4. 3 to 4. Rest everything is 0. like this. Correct? Now you see, once you have accessed a given element, okay, next what you have to do is you have to go row by row, right? Row by row, sort of row by row you will go. So what happens is you have to, you know, delete off that element from the queue. Once you do the operation on it, then you will have to remove it from the queue. So that is done by using front plus plus. Next, you will have to check if it is, you see, this is an adjacency matrix. See, it is going row by row. So only I equal to 1, I less than or equal to an I plus plus is present. Then what you do is you check whether the value is 1. That means if there exists a path. So if there is existing a path, and if the visited is still not if it is still 0, that means if the node is not visited and there exists a path, then what you have to do, you have to add that to the queue, right? You have to add that to the queue and immediately make that visited as 1, and then you have to print the value whatever you have just accessed. Okay, now let me again explain you. See, in case of BFS, the traversal happens horizontally. Okay, and we make use of a data structure called as queue. Okay, we make use of a data structure called as queue. Now, in order to start the traversal, we give the starting vertex. So when we give the starting vertex, that vertex would become something called as visited. So we are setting the visited equal to 1 for that particular vertex. Similarly, we will do for other vertex once we access them. Now, once we visit them, then we add it into the queue. Okay, we add it into the queue. Next, one element is added into the queue. Okay, while front is not equal to red, that means when your queue is not empty. See, your queue is not sort of, empty. Okay, then what you're supposed to do, every time you put an element into the queue, when you do the next iteration, this will get popped out also. Because from there you will access the neighbors, right? So you don't need that variable. Once you have visited, you have accessed its numbers, done. Next time you don't need it, so you will delete it off. Next, from the given vertex, from the given row, you want to check if the next vertex is visited or not, only if there is a path existing between them. Otherwise, you simply don't have to go from 1 to 4, because 1 to 4, there is no path existing, right? Though 4 is not, see here. See, in this case, when I visit 1, okay, next possible value is 2, right? Why is it not 4? 4 is also still not accessed, because these two conditions has to be fulfilled. Current of I is equal to 1 and visited is equal to 0. Visited means not accessed, and if there exists a path. If so, you add it into the queue. You immediately make its visited as 1, so that next time you don't have to access it, and then you print the value. That is all about the BFS. Similarly, for DFS, DFS makes use of stack. So we start with the given vertex. Then we make its visited as 1. When we start with the vertex, we make it as 1. Then we put it onto the stack. We increase the value of top by 1 and then put V into that. Then again we check from V to I, whatever your, so it will go like this, right? So column. Okay. So we check for the column. If it is, if there exists a path and if it is still not accessed, then we print the value and we do the DFS all over again. Okay, that is the concept of DFS, depth first search. Whatever we have visited, immediately we have to make it 1 and put it onto the stack. Okay, put it onto the stack. Okay. And next time when you want to access the element, there should be a path and it should not be visited. That is what you can do. But here only one element can be taken at a time. Okay, this is all about the lab program 11. Sorry, I hope you have understood. I have a separate video about how BFS and DFS works with the help of an examples, much more examples and manual calculations. So you can go through them if you want the explanation of it. Okay. Thank you so much. I hope you have understood. Thank you so much.